Hello, everyone. My name is Nishant, and today I will be presenting our work titled Towards Understanding and Detecting Cyberbullying in Real-World Images, carried out in collaboration at the University at Buffalo and Clemson University. Traditional cyberbullying is a well-known phenomenon. Researchers today are well aware of its factors, such as the use of harmful words and phrases by perpetrators of cyberbullying. Consequently, traditional cyberbullying based on text can be detected by state-of-the-art detectors with high precision. Traditional cyberbullying is also a well-researched problem witnessed by a large body of work in this domain, in various fields such as psychology and sociology, in addition to computer science. However, the existing solutions focus on only text-based cyberbullying, while largely overlooking cyberbullying perpetrated in other forms of media, such as images. Recently, there are two emerging trends in resource sharing on the internet. First, new internet technologies, such as smartphones and cameras, have emerged, which can enable users to conveniently capture visual media, such as images. Second, new internet platforms have emerged that are focused on image sharing, such as Instagram, Flickr, and Facebook. Perpetrators use these new technologies and platforms to send cyberbullying images to victims' devices. Thus, cyberbullying in images has emerged as a new phenomenon plaguing today's internet. There is an urgent need, therefore, to study the new issue of cyberbullying in images. Specifically, the detection, understanding, and factors of cyberbullying in images should be deeply studied. In our work, we focus on the new problem of cyberbullying in images, study its factors, and introduce techniques to effectively detect this new problem. A major issue is that in order to study cyberbullying, we need to first understand its factors. For example, in traditional cyberbullying, some factors are described as the use of harassing words or phrases, name-calling, and humiliating insults. However, for cyberbullying in images, its factors should be studied in detail. To fully protect against cyberbullying in images, we need an understanding of its visual factors. Another issue is that in order to defend against cyberbullying, we need techniques that can effectively detect it. In case of traditional cyberbullying, a significant number of detection systems are available, such as Perspective API, Amazon Recognition, and IBM's Toxic Comments Classifier, which achieve accurate detection capabilities. However, there is a lack of such systems that can detect cyberbullying in images. For example, the existing systems that can detect image offensiveness, such as Google Cloud Vision API, Amazon Recognition, and Clarify NSFW, could not detect the sample depicted on the screen. In fact, we found that 39.32% of the cyberbullying samples from our dataset circumvented all existing detectors. Thus, to effectively defend against cyberbullying in images, there is a need for its effective detection. For effective detection of cyberbullying in images, the context of the image should be considered, since cyberbullying is a contextual problem. The performance of the existing systems was found to be quite low for detection of cyberbullying in images. Additionally, we found that the existing systems did not take the image context into consideration, as seen in this example, wherein the first image does not have much context, but the second image depicts the context of a person pointing a gun at the viewer. All the existing detectors treat the two types of images similarly, as can be seen by the similar scores for the two image samples. In summary, the existing systems' detection capabilities was found to be not sufficiently accurate and not contextual. Thus, we need accurate and contextual detection of cyberbullying for its effective mitigation. In this paper, our objective is to understand cyberbullying in images and enable its contextual detection. Understanding it requires cataloging its visual factors, and contextual detection requires efficient detection of cyberbullying with the image context. However, to achieve understanding of cyberbullying in images and enable its contextual detection, there are two key challenges to be addressed. The first challenge is the unavailability of cyberbullying images dataset. We need such a dataset for training a classifier that can detect cyberbullying images, and we also need such a dataset to understand cyberbullying in images. However, collecting such a dataset is not an easy job, since the dataset should be sufficiently large. it should be representative of real-world cyberbullying, and new strategies should be developed to compile it. The second challenge is to catalog the visual factors in order to detect and understand cyberbullying in images. However, this is not a straightforward task, as there could be multiple such visual factors. Thus, we need to find the visual factors of cyberbullying in images, build detection systems based on these factors, and evaluate the effectiveness of these factors. To address the challenges of the unavailability of cyberbullying dataset, we introduce a novel strategy to collect such a dataset. We use anonymous self-reported stories of cyberbullying from users with cyberbullying experiences to first compile a set of keywords. From the reported stories, we perform preliminary cleaning tasks such as removing stop words and filtering negative sentiment words, which finally left us with 378 keywords. Next, we use those keywords to crawl images from search engines and as well as social media websites and collected 19,300 potential cyberbullying images. Then we conducted a study with participants from Amazon Mechanical Turk to label the images as cyberbullying and non-cyberbullying. Finally, our dataset consisted of 4,719 images of cyberbullying. We next discuss our approach. We have cataloged 5 factors of cyberbullying in images. First, we consider the body pose of the person in the image. We observed that images depicting persons who pose at the viewer had strong correlation with cyberbullying images. In contrast, these images with the person posing at the viewer were observed to have a much lower correlation with non-cyberbullying images. We used open pose to estimate the body pose of a person in the image. Open pose detects 18 regions of a person and outputs the detected regions and their corresponding detection confidence. We use the confidence scores of the regions as the factor values. Second, we use the facial emotions of the person in the image. Facial emotions have been known to convey significant meaning regarding what a person is feeling. We observed that subjects in cyberbullying images generally showed positive emotions such as joy. We extracted the facial emotions in our dataset using 2 sources, OpenFace and Google Cloud Vision API. We chose the emotion categories that are indicated with high confidence by both these sources. Overall, we use 4 emotion categories: joy, sorrow, anger, and surprise. Third, we use the hand gestures shown by the person in the image. We find a high correlation of hand gestures, for example, loser, middle finger, thumbs down, and gun point, with cyberbullying images, indicating that hand gestures are an important factor. We use the tag suggestions by Google Cloud Vision API to indicate if an image depicts any hand gestures. Fourth, we use the presence of certain objects in the image as a factor. We observed a correlation of threatening objects such as guns and knives with cyberbullying images, which indicates internet users may use these objects to threaten or intimidate a viewer. We use an open source object detection system called YOLO to detect the objects in images of our dataset. YOLO outputs the object category as well as the confidence score of detection for each object depicted in an image. Finally, we considered social factors of cyberbullying, as cyberbullying is a deeply concerning social issue. We analyzed the cyberbullying images in our dataset for current social-related factors such as anti-LGBT and racism. We found that images depicted anti-LGBT symbolism and blackface and historical references to hanging. Since detecting such social factors in images is a complex task, we directly labeled the images that contained such symbolism in our dataset. Next, we discuss the classifier models that have been formulated to detect cyberbullying in our work. The cyberbullying data broadly consists of low-level image features and the cyberbullying factors discussed in this work. We study the classifier models to not only effectively detect cyberbullying in images, but also to study the different features that are important in classifying cyberbullying in images. The first classifier is the baseline model, which is based on the untrained VGG16, a popular convolutional neural network. We directly trained the baseline model with the low-level image features. Our intuition behind choosing this baseline model is because we want to include use cases that are common among most of the existing detectors. The second classifier is a multi-layer perceptron that is trained on the cyberbullying factors only. Our objective was to investigate whether the factors identified alone could be used with no image features to classify images as cyberbullying versus non-cyberbullying. The third classifier model is based on a VGG16 model pre-trained on the ImageNet dataset and fine-tuned for detecting cyberbullying. Fine-tuning is analogous to how humans use knowledge learned in one task to solve new problems. We only provide the low-level image features for training this model. The fourth model is a multimodal model that combines the low-level image features with the usual factors of cyberbullying. The architecture of this model is depicted in this slide. We use the VGG16 pre-trained model for image features and use a multi-layer perceptron model for the factors-related features and combine the feature vectors from both these models using lake fusion. We evaluate the cyberbullying visual factors and the classifier models from several different perspectives. We study the effectiveness of the visual factors of cyberbullying by understanding their effectiveness. We conduct a measurement of the classifiers introduced in this work by studying the effectiveness of classifier models and by studying the capabilities of the existing offensive image detectors. We study the performance overhead of cyberbullying image classifiers by deploying the multimodal classifier in a mobile device and measuring the execution times. We first studied the frequency of the visual factors in cyberbullying images. For cyberbullying images, we note that certain factors occur frequently in cyberbullying images. For example, body pose accounts for 76.91% of images and gesture 50.6%. Next, we studied the associations between human-level annotations on images and the identified factors by analyzing the correlations for visual factors and cyberbullying images. We found that certain factors showed strong associations with cyberbullying images. For example, a correlation of 0.39 is observed in case of the body pose, indicating that annotators tend to agree that a subject in a cyberbullying image intentionally poses at a viewer. Thus, certain visual factors are highly correlated with cyberbullying images. In our next study, we conducted exploratory factor analysis to discover the uncorrelated factor sets that are most effective in distinguishing cyberbullying images. The scree plot depicted in the figure suggests the number of factors to extract. The next figure exhibits the factor loadings after varimax rotation. A feature is associated with the factor with which it has a higher loading than the other, and features associated with the same factor are grouped together for certain descriptive categories. Intuitively, cyberbullying in images could be characterized with two social constructs, post-context and intent context. To study the effectiveness of the different classifier models, we perform the receiver operating characteristics analysis of the classifier models. The area under the curve of each classifier model is depicted in the plots, which indicates the success of a model in detecting cyberbullying images. We found that the multimodal classifier demonstrates the highest performance with a precision of 94.27% and recall of 96.93%. We then studied the capabilities of the existing offensive image detectors on the visual factors found in our work to analyze how easily the existing detectors can be extended to address cyberbullying in images. We found that the body pose factor can be addressed by Amazon Recognition. The facial emotions factor can be addressed by Google API as well as Amazon Recognition. Hand gesture factor can be addressed by Google API. Threatening object factor can be addressed by Google API, Deep AI, and Amazon Recognition, and social factor cannot be currently sufficiently addressed. Thus, existing systems that detect image offensiveness can be extended to also detect cyberbullying in images. We studied the performance overhead of the multimodal classifier if deployed in the real world by deploying it in an Android application, running in a Samsung Galaxy S5 model device. We calculated the model time, which is the execution time for a forward pass of the multimodal model, and the render time, which is the execution time for secondary tasks, such as resizing the input image and showing warnings. We found that the average model time was 753 milliseconds and the average render time was 0.06 milliseconds, both of which are sufficiently low. To conclude, we propose a study of cyberbullying in images, wherein we studied its visual factors and developed classifiers to detect this problem. We cataloged 5 factors of cyberbullying in images and designed 4 classifier models for its detection and conducted extensive evaluation of our approach. For our future work, We will investigate methods of cyberbullying in other contexts, such as image together with text. We have also planned to develop a suite of tools for multifaceted detection of cyberbullying. Thank you. We welcome any questions from the audience.